Okay, some sample problems for chapter 29. First, let's take a look at problem number 16, which is a problem on Lenz's law. Made the figure a little bit bigger, go big or go home. And we're going to have some current flowing through this wire right here. And we're told that the current is going to start decreasing exponentially over time because t is going to be larger than 0 and b is larger than 0 as well. And we're asked for what is the direction of the current induced after the current in this little ring right here after the current starts to decrease. So it's going to oppose a change in magnetic flux. Let's take a look at the magnetic field caused by this current right here. Take my thumb, point it in the direction of the current, and you see my fingers are going to kind of curl around like that. So the magnetic field is going to be essentially out of the page through this coil. Now the current is going to start to get smaller. This magnetic field is going to start to get smaller and smaller and smaller, and the current induced is going to oppose that. So it's going to essentially want to keep a magnetic field coming out of the page. So I take my thumb and I point it out of the page. Which direction do my fingers curl? Well, they're going to curl in that direction. And so the induced current is going to be in that direction, and so it's going to be in the counterclockwise direction. Okay, another example of Lenz's law as well as calculation of induced EMF. Example 29. Here we have a rod that's connected across a kind of like the slide wire generator, and we're told that we have some force that's being applied that's going to keep this bar flowing at a constant velocity. Essentially what we have is we have a changing flux. Remember that the flux is going to be equal to magnetic field multiplied by area, and here the area is going to be getting smaller and smaller and smaller and smaller, so we're going to induce a current that's going to try to oppose that change. Essentially it tries to keep the flux to be equal as constant as possible, so essentially it's going to have this magnetic field that's going to try to bolster up this magnetic field that's pointing out of the page. So the direction of the current, well, we take our thumb and we point it in the direction of the magnetic field, so we're looking end on at our thumb. And we can see that it's going to have a current that's going to be in the counterclockwise direction. Now for part B, we're looking for the rate at which the applied force is doing work. Well, we're looking for the work divided by time. That's also going to be equal to the power. Now the work, that's going to be the force multiplied by the distance divided by time, thinking back to physics 241. And actually we don't really know the distance or the time. However, distance divided by time, assuming that it's at a constant velocity, is going to be the force multiplied by the velocity. So we know essentially what that velocity is. Now we need to say, okay, well, let's figure out what the force is going to be. We know that the magnetic force is going to be equal to the current length crossed with the magnetic field. It's all perpendicular, so we're just left with ILB. We know the length and we know the magnetic field, so now we need what the current is going to be. Well, we can say induced current is going to be equal to the induced EMF divided by the resistance. We know what the resistance is, now we have to figure out what the EMF is. EMF is simply going to be equal to the magnetic field multiplied by the velocity multiplied by the length. Divide that guy by the resistance. And so at the end of the day we can plug all this together and say that this force is going to be equal to the velocity multiplied by the magnetic field squared multiplied by the length squared divided by the resistance. And so the power is now going to be that force multiplied again by velocity, so we're going to have a velocity squared, magnetic field squared, length squared, and resistance squared. So we're going to have essentially 5.9 meters per second, that's the velocity. We're going to have magnetic field 0.65 Tesla. Oops, make sure I square that guy. And then the length is 0.36. Square that guy, and then the resistance is 45 ohms, and we're left with a power output which is actually quite small, 0.04 to 4 units are going to be watts. And essentially what that's saying is that this generator is not the most efficient generator in the world. Okay, some solved problems for chapter 31. Here we have a step-up transformer where we essentially have some household voltage of 120 volts. It's connected to a neon sign that's running 13,000 volts, fairly typical for a neon sign. 13,000 volts. And we're asked for what is the ratio of the secondary to primary coils. So what is that guy going to be equal to? Well, that's just going to be the secondary voltage divided by the primary voltage, or 13,000 volts divided by 120 volts. So we're left with this ratio, N2 over N1 is going to be 108.3 turns, or 108.3. Now for part B, we're asked for what is the power that must be supplied when the secondary current is going to reach its limiting fuse. Well, we know that power is simply going to be equal to current multiplied by voltage. In the case of AC, it's kind of an average power, but the same equation is going to apply. So we're going to have 8.5 times 10 to the minus 3, that's the limiting current. And we know that we're running it at 13,000 volts. And so we're going to get this average power to be 110.5 watts. Now part C, it says what current rating should the fuse in the primary circuit have. Turns out that the power and the energy are going to be identical in the primary and the secondary, and so in that case the power in the primary is going to be equal to kind of this power in the secondary. So we can use the same equation to say that the current in the limiting current in the first is going to be equal to P1, which is equal to P2, divided by the primary voltage, so 110.5 watts divided by 120 volts, and we're going to run up with 0.92 amps. And lastly, let's take a quick little trip over to Europe, where all of their outlets run at 240 volts as opposed to the 120 volts that we typically have in the US. Well, we're asked, well, what can we do to operate this dryer on the 240 volt line? Well, we know we're going to have some initial voltage of 120 volts, and we want to make this guy operate on a 240 volt circuit. So what we need to do is we need to have a step-up transformer where we can say N2 over N1 is going to be equal to V2 over V1, so 240 volts divided by 120 volts. So this says N2 is going to be equal to N2 over N1 is going to be equal to 2, so essentially we have twice as many loops on the secondary that we do in the primary. So now we're asked what type of current we're going to draw. Well, we know the power rating of this dryer, we know the voltage that we're going to be operating it at, and we are asked what is the current going to be equal to. Well, current is just going to be equal to the power divided by the voltage, so 1600 watts is the power rating on it, and then the voltage is going to be 240 volts. So we're going to be drawing 6.67 amps over in Europe. Lastly, we're asked for what is the effective resistance of the dryer. Well, we know that the power can be written as the square of the current multiplied by the resistance. So the resistance is simply going to be equal to the power divided by the current squared, or 1600 watts divided by that 6.67 squared. And we're going to have an effective resistance of 35.96 ohms.